So let's dig into this kind of idea of this transition state a little bit more, because it's kind of weird and nebulous to think about what is actually going on at that peak of activation energy, right? We're at the most energy internal to our system. What is actually happening in terms of the particles? We got to step back and think about what it means in order for a reaction to occur. In order for a reaction to occur, your particles have to collide. You got to have two kind of different particles come into contact, hit with enough energy in the right orientation, in the right way to get one bond to break, while at the same time forming another bond. And so atoms and molecules, or ions, must collide with each other in order to react. That's what we mean when we say the collision theory, the theory that things got to collide in order for things to happen. Increasing your temperature increases the frequency of the collisions. We know that they're going to collide more often, and it increases the force of those collisions. So we actually see a twofold reason why our rate increases when we start to increase that temperature. Here we've got kind of two particles trying to collide, but we've got the red versus red, not going to go. Here we've got, again, kind of the three on side, red coming in to collide isn't going to work. Here we're not quite lined up right in order to get our bonds to peel away. So this is, sorry, a hydronium. This is a hydroxide. We're trying to make two water molecules. And so we need to get this kind of the hydroxide to rotate just a little bit in order for it to collide with that hydrogen in just the right orientation with just the right amount of energy to get this water to leave and have another water break off. And so there's a lot of factors that kind of go into this collision idea. And we measure that. We measure how much energy it takes for this reaction to go. We call that the activation energy, or EA. It is the minimum energy needed to break those bonds in the reactants so they can then go ahead and change the bonds or form the bonds in the products. Increasing the temperature only increases the number of effective collisions. It does not lower the activation energy. Activation energy is the bonds, and those will always be the same. If we're thinking about, and this is the Boltzmann distribution, some of my physics people may have seen this. If we're thinking about activation energy, the minimum energy needed for the reaction to occur, that's here. That's a finite value. I gotta have this much energy to break them and then reform. If I increase the temperature, so we had T1, we're thinking about the number of kind of viable collisions. So here we had a colder temperature. We heat them up, now we've got a higher temperature. You'll notice that we have more area under the curve for that higher temperature. We do not change the activation energy. We just have more particles now that can get over the activation energy. Note the difference. This one gets frequently confused and kind of misused. And so make sure you're paying attention to what we're saying here in terms of activation energy stays the same. Temp just gets more particles over that hurdle. Cool. Transition states are weird. So like if we're looking at this carbon here for just that split second, it was originally bonded to this bromine. Well, we got to break those bonds right as we start to form these oxygen bonds. And so for just this briefest moment, this carbon's got 4.5 bonds, 5 bonds. Looks like there's 5 things bonded to that carbon. It doesn't like that. That's why it has such a high energy at the transition state. And they like to sneak this onto assessments for example, for an exothermic reaction, which has more internal energy. Is it reactants, products, transition states? Cannot be determined. It is always going to be your transition state. Don't let the endo and exo part fool you. That transition state is always going to have the highest energy because it is the most unstable molecular particle in your reaction. So transition states occur when we have enough energy to get that effective collision that we're actually going to hit, make some bonds and break some bonds. You got to have the right orientation. You got to have the right number of the molecules. You got to have the right amount of kinetic energy to get them to hit and collide close enough to break and form and all that good stuff. Transition states are very high energy and very unstable and exist for fractions of a second. And so they're really hard to model and understand. And so we do our best to kind of come up with an understanding of what this would have to look like in order for this to occur. But it is really kind of weird to think about, okay, now we got a carbon with 5 bonds. And in our transition state, we see properties of both bonds for our reactants and our products. And this is why we call it the transition state. This is where it's actually changing from one to the other. Sorry, if you need to pause video, come on back and get all these notes down. Cool. So if we're going to show this without all the pictures, sometimes we'll show it in our three-dimensional 2D drawing. So our arrows here are just indicating to us that one hydrogen is in front of the board and one hydrogen is behind the board if we're thinking in three-dimensional space. So here's our original tetrahedral molecule. Our hydroxide's coming up. And then for a right before we start to transition, we see that our hydrogens start to get pushed back a little bit. We've got now this kind of pseudo bond where the bromine is breaking and our hydroxide is forming. Right there in the middle, we've actually got these hydrogens kind of parallel. We've kind of talked about this. This is the trigonal bipyramidal molecule where we've got 5 of the 7. But again, we know carbon doesn't really want to do that because it only wants 4 bonds. And then after our transition state, we start to see kind of an inversion of our molecule. Sorry, I'm trying to move this so we're not in the way. Where now our hydrogen have swung to the other side and our hydroxide is now there on the other side. In organic chemistry, you'll learn all about E1 and E2 and SN1 and SN2. Don't worry about that here. We're just kind of thinking about what this means in terms of our transition states. So cool. And we can also relate that to our energy. If we're thinking about our particles, here's our starting reactants. We've got lower internal energy here after. So final mass initial, that'd be negative. This is an exothermic process. Our highest state is at that full transition state. And we can actually see as we're gaining more and more instability, where we're kind of that EA forward versus our EA reverse, and we're starting to release that energy back out as we form our stable products. So thinking about this transition state and how we can apply that back to our energy diagrams and what this means for us in terms of what's actually happening to those bonds. Cool, just another example, couple more examples for you. Here we've got 2 NOCl2s. So here's the first NOCl, here's the second NOCl. We're forming these bonds. We're breaking these bonds right here at this transition state. Here we started with nitrogen monoxide and ozone. So here's our nitrogen monoxide. Here's the original molecule. Here's the ozone original molecule. We're forming these bonds to the NO and we're breaking the ozone apart. So we're kind of forming and breaking all at the same time. And so everything's kind of together and reacting. Another one here, we've got 2 CLOs. So first reactant, second reactant. We're forming the chlorines, forming the oxygens while breaking the chlorine oxygen bond. So we've actually got kind of 4 species going on all at the same time. Lots to be kind of thinking about here. We're going to do a bunch of examples here. Just want to get this in your head and kind of percolating and thinking about what this would look like. We'll spend some more time looking at transition states and kind of making sure we're getting this locked up before we move forward. Cool. Thanks, guys.